Okay, so what we are talking about here is the Savage and Hubbard top 10 list of lame excuses for not quantifying uncertainty. And the story here is that as Doug and I got to know each other, we discovered that we were telling the same stupid jokes to get people over the same stupid hurdles, right? And so at some point I thought, all these people are dragging their feet and we need a top 10 list. And the list itself is actually out at flawofaverages.com. But here comes the first one. Is this big enough? So
yes,
our situation is too complex to model. So we do it in our head based on experience. And I'll just read both of our comments under here. So Doug says, if you're doing it in your head, you are using a model. Calibrate your own estimates, then compare them to other modeling methods.
Mm-hmm.
You'll be surprised how inconsistent you are without quantitative measures. And I say, even if the model does not give you the right answer, the very act of modeling often leads to the right question. So that's number 10 on the list, and let's riff off of that for a while.
Yes.
Our situation is too complex to model, so we just do it in our head.
And I think you've put it very mildly for the questions. This is some of the most common excuses for inaction on why people do not try and apply quantitative risk analysis or do not move to stochastic models and stay with the single point estimate. So this is a very common excuse that I also hear at conferences and whenever we share how we've done our models. And this is, by the way, this is the last funniest thing I heard. We did a whole workshop on how we were improving our budgeting at the chemical plants through better operational risk analysis. And we showed how we decomposed operational risk into 5 different elements, and then we modeled each one individually and then aggregated the models because SIPMath standard allows us to do all that mathematically correctly. And the comments that I heard in the comment section when we were doing this workshop said that our business processes are significantly more complex and hence this is not applicable, which of course couldn't be further from the truth because our business processes are probably very complex, but then we took a lot of effort to first convert the reality into a model. We were finding why was it 5 components, we had 7 components to the operational risk initially, and then we settled on the 5 because we had the best data for the 5 and we were able to clean it. And so that is such a ingrained misconception, I think, in decision making that somehow reality is just unmodelable.
Exactly. There's a new book, fairly recent book out called Radical Uncertainty.
Yes,
okay?
I read it.
Okay, and I'm afraid my comment about the book is it's 50 pages of really interesting material packed into a 500-page book, but there's a lot of truth in there. But what it reminds me of, it's the world's too complex, we can't do it. It reminds me of Nicholas Taleb's ludic principle.
Mm-hmm.
Remember what that is? He says ludic is from Latin meaning playing games. So Taleb says you can't model things like the stock market using spinners or dice. That's the ludic principle. I agree with it. He calls it the ludic fallacy.
Uh-huh.
That's the ludic fallacy. My own version, though, and I believe in that, but mine is the ludic fallacy. Uh-huh. You can model stock markets or weather without understanding spinners and dice. It's like accounting. You can't be an accountant if you don't. If you only know how to add 1 + 1, right? But you can't be an accountant if you don't know how to add 1 + 1. And you have to start somewhere because this thing down here that by the modeling you start asking the right questions.
You're absolutely right, and I completely agree with that. And that kind of really brings us to the comment that Doug made on this, and he calls it "beat the bear fallacy." When we start with nothing,
the bear fallacy is further down.
We'll come to that as well. But there's basically when you start with nothing, when you start with the model, your mental model, what's in your head, you have to compare it to the simple mathematical model, and there appears to be, again, everybody can backtest it for themselves, and they should in fact backtest it, but there appears to be enough evidence to suggest that even the most simplistic model still outperforms your mental model. And in
Right.
fact, it's not that difficult to outperform your mental model. And then you can kind of start building on that. And of course, you can't jump from nothing to the amazing complexity. And in fact, if example of weather forecasting, I think was any indication, the more complex the model got, the more model error they obtained. And in fact, it was less predictive, it had less predictive power. And they scaled back to the slightly more simpler versions that they had in the middle. That is also a conclusion. But when you start with nothing,
Yes.
don't expect to jump to perfect world model. It's, you know, you have to iteratively move to MVP, then upgraded MVP, and then kind of you improve your predictive power, the predictive power of your model every iteration.
Well, and I think Doug has done stuff like this as well. Of course, he's very big on calibration, which is just great. He gets people together, and he didn't invent this, but he's learned a lot from it. In which you get a bunch of people together, you ask them some trivial question. It's like, how tall is the Eiffel Tower in millimeters? And you get a range, and people say, well, I'm 90% confidence between this and this, and by doing that, people are very consistently wrong on these sorts of things, and they are very consistently narrow in their ranges of uncertainties. And he's shown that through calibration, you can improve this. But also, if you then run regression models off of what experts say, those regression models are better than the experts because you've taken the statistics into account. And I think I just keep coming back to radical uncertainty, which in a sense was so dismissive of doing modeling because you don't catch the stock market crashes and things.
Yeah.
And the point is just don't, that's part of modeling maturity, is to know what you can or cannot capture. In fact, you mentioned weather. This takes us to a situation that is too complex to model with a model, and weather is one of them. So are you familiar with chaos theory?
Yeah.
There are things in life where tiny changes to the input assumptions make huge changes in the output. The famous butterfly effect. So, why did a tornado end up in Kansas instead of Nebraska? Well, it's because when a butterfly took off from a daisy in Texas, it turned right instead of left. And it turns out that this was discovered in the early 60s, I think, at MIT, where they were running gigantic weather simulations.
Mm-hmm.
And they figured weather is just physics. Physics is deterministic at this scale. We're not at the quantum mechanical level. So, hey, we have the current temperature, current pressure, this, that. We run it and see where it goes. And so in those days, it was like printing out reams and reams of paper. And, every row of the simulation was probably, this is what the pressure is, the temperature, the wind direction, the da-da-da. And at one point, as happened in those days, the computer would crash. And they said, oh my gosh, we've been running it for 12 hours. We don't want to start from scratch. So what they did was they backed up like half an hour into the simulation. And they had all the state variables, all the pressures and temperatures and everything. And they just used those as the boundary conditions then to move forward, right? Because they didn't want to rerun the whole 12 hours. Well, they did that. But then that last half hour of simulation or whatever it was, they got completely different results. Well, that can't be. We put in the same boundary conditions. No, you only put them into like 15 decimal places. And this is the kind of thing where, the changes at the 85th decimal place mess you up. Well, they didn't know. But I mean, this was really kind of the clue that chaos theory existed. And I think it is. And by the way, it exists in many, many places when you have non-linearities, right? So as we get into modeling, it is important for us to understand where the chaotic boundaries are. It's an important concept for people to understand. For example, I used to be a pilot, and there are places where planes fly very predictably. And there are places where they go chaotic. When you stall an airplane, you don't know if it's going to spin right or spin left or do this or do that. It has to do with turbulent flow of the aerodynamics, which is also a well-known chaotic phenomenon. So I think part of this, our situation is too complex. Actually, your situation isn't. You should see where the complex ones are and know those boundaries. And that's where you're going to stop modeling, not just on,
I have, so that, and I like your idea of complexity boundary when it switches off, because I had an instance where a board member was very dismissive of the results of the simulation because he said, but it didn't predict X and Y. And that was a very kind of, that was a mental trigger that started me thinking. And what I've discovered for myself, and tell me if you agree or disagree with this. Every distribution, every distribution has a body and the tail, and this difference between the body and the tail is where you move your confidence interval, your confidence level. For example, building a model that is okay 90% of the time is not that difficult. But building a model that is okay 99% of the time is actually ridiculously difficult, because the relationship on the tail starts changing quite significantly. Like, that's where the boundary of chaos kicks in, and you cannot longer use the same distribution. And so when this board member said that you haven't accounted for such and such, and we said, but we weren't planning to, because we were building a model for a 95% confidence interval. And this specific event happens once every God knows how many years. Right. And it was never meant to be included in our model.
Well, so that is, again, a very profound direction you're headed here, which goes back to this word complex, all right? And so there are some examples. My favorite is the example of the law of averages, where the drunk is wandering back and forth on a busy highway, and his average position is the center line. So at his average position, he's alive, but on average, he's dead. That is one where it should be criminally negligent not to simulate. It does involve the tails of the distribution. There are so many things that Jensen's inequality, which I call the strong form of the law of averages, absolutely affects. The profit of the average demand is going to be less than or greater than the average profit. You need to know that. And it does not matter what distribution you use. So there are all these things where there are inequalities.
Yeah.
It's going to be bigger than that, guaranteed, right? Or smaller than that, guaranteed. There is absolutely no excuse not to go after those. Now, as you get towards the chaotic boundaries, this is something that I want to show you that we've done here that relates to complexity. The thing is too complex to model, right? And you were saying, right, the distribution has a body and a tail. And my response is absolutely right. I don't want to start with the tails, because there's so many places with a body that you guys are just out to lunch. You know, you thought there's a 50-50 chance of this project finishing in 6 weeks. There's one chance in 1,000 it'll finish in 6 weeks. And it doesn't even matter what the distribution is. It's just because it's like flipping 10 heads in a row on a coin. So one of the things to kind of guide us in our complexity assessment, we should call this, is in the chance calc settings. Chance calc is designed to give us the chance of something happening. And you have your choice to round the probability down. Like, okay, 5%. We don't recognize anything small. So it's 0, or it's 5%, or it's 10%, or it's 15%. You could crank that up to 50%. Maybe, well, it's either more likely or less likely to happen than a coin flip.
Yeah.
And that is a kind of maturity that does require training. But there is this famous example in military readiness where it wasn't too complex. Operation Eagle Claw. In 1980, the staff of the U.S. Embassy in Iran was held hostage. And they launched this Operation Eagle Claw to rescue them. And they needed 6 helicopters operational to complete the mission. And the helicopters were 75% dependable. There's a name for this. Mission capable rate, right? Okay. So they sent 8 because 75% of 8 is 6. And that would have gotten them 6 helicopters on average. But Jacob Bernoulli, 300 years earlier, with his binomial distribution, would have predicted there was one chance in 3 of not having enough helicopters. And, that's like the chance of rolling a 1 or a 2 on a die makes this most important mission since World War II fail. Did I need to know that it was like 33%, 34%? No.
Yeah, exactly.
Bigger than 15%. I mean, so I think that's one of the things that we need to train people in, is this whole notion of degree of complexity of the model and where to, in effect, back off because people always say, well, you did not model the fact that there was a tornado in Nebraska instead of Kansas.
Yeah.
But we're not claiming to.
Well, that's exactly it, and I think you've raised a very important message. And the second kind of takeaway from that I had is that your approach to dealing with the risks in the body and in the tail is very different anyway. And for example, you insure against the tail because you're probably not going to have enough capital to reserve for it, and you're not going to be able to mitigate it to non-existence.
Right.
And the body. That's where a lot of value is sitting, because you can improve your decision making, the quality of your decision making, your budgeting, or forecasting, or planning so significantly without even worrying the tails for the time being. Because for the tails, you need to collect all the tails kind of in one place and then have a sit down and think, well, what can we insure? What can we hedge? What can we reserve?
Right.
And it's even a different discipline. It's business continuity management versus risk management.
Yeah, I mean, with Operation Eagle Claw, they were at the 66th percentile, right? They didn't model against the 66th percentile. I mean, it's nuts, and you see it all the time in project management when people don't understand if there's any uncertainty at all, this thing is going to be delayed.
So let's rephrase that response to that excuse, because this is a common excuse. People say, "Oh, the business is too complex." Of course, it is too complex. It is too complex to model to the 99.999 confidence interval. But you can save millions of dollars modeling to 60th percentile, and you can still save millions of dollars. So, what would you prefer? Save millions of dollars at the 60th percentile, or save more millions of dollars but at the 99th percentile, but spend 10 times the effort of modeling the business?
Exactly. And there's a wonderful quote I think we could finish up with from John von Neumann, greatest mathematician of the 20th century, invented the computer. If people do not believe that mathematics is simple, it is only because they do not realize how complicated life is.
Yes, that is very true.
And von Neumann was the greatest mathematician of the 20th century and inventor of the computer and a bunch of other things. So Alex, I always have so much fun. I learn so much when we get together. It's sort of like a jam session when I used to play music, right? We're just basically, it's like statistical jazz or something that we're playing together.
I like that, statistical jazz. Thank you very much, Sam. And I hope everybody enjoyed this short video, and we'll do more of this.